Okay, so again, VSEPR theory, all right? Theory behind VSEPR theory is light charges repel, bonds repel, and they'll form the shape of the molecule, okay? We're going to try and get through 3 more shapes, and we'll see how we go with this one. All right, the next set looks at slightly differences, or a minor difference between the 2 that we've done so far. So what I think I'll do is we will look at the structures first. And we'll give you some examples of these molecules. There's one. Okay. And we'll explore that structure. Okay, now, the next one is based on this particular molecule, which is ammonia. Okay? And again, it is actually based on, if I ask you how many groups of electrons in total, how many groups are we talking about with an ammonia, Joey? 4. Okay? There is 1 non-bonding, there it is, and there are 3 bonding sets. But in total, there are 4 groups of electrons. And hopefully you'll begin to possibly make some connections in a minute. So this one here is based on 4 groups of electrons. 3 of them have got bonds. Now 3 of them have got bonds. When we look at the shape of this molecule, okay, and if you were to imagine that as being an actual shape, it forms a trigonal pyramid shape. All right, so you all know what a pyramid is. You know what a 4-sided pyramid is. This one, all right, forms a trigonal pyramid. So it would be this idea, okay, is what we're talking about. So that's a shape, all right, of an ammonia molecule. Now the nitrogen is here. If you can't visualise it, there's a nitrogen, there's a hydrogen, and a hydrogen, and a hydrogen. It's much easier to look at it in 3-dimensional space. Okay? So again, here is our non-bonding pair. And we said anything that's non-bonding moves around. And so it actually forms, or pushes, the 3 hydrogens downward. It doesn't really matter. You could say that they push them up. There's no up or down in the molecule. Okay, but certainly it affects the shape of the molecule, okay, overall. We call that shape trigonal pyramid. So there's another shape that we need to understand. This one here is trigonal pyramid. Alright, we're going to get rid of some of the molecules over here, some of the linear structures, okay, and we will go a little bit further with our shapes, we hope. Alright, so trigonal pyramid, 4 sets, or 4 groups, 3 bonding, 1 non-bonding. Okay, the next one involves, again I think I'll need to draw it for you, so the first thing is, what does it sort of look like in 3-dimensional space? And that's what it looks like. The example of the molecule is actually boron trichloride, and it's the only molecule, or it's one of the only molecules like it. Okay? There is another one that looks like this, and this structure, I won't ask you to do it, it's a bit complex. Okay? I've got bits of it here. Alright, that one there is sulfur trioxide. We could build it, okay, because it actually comes from sulfuric acid. So all I need to do is just grab another double bond, get rid of that hydrogen, and I've got an oxygen here, and I've got an oxygen there. Alright? And so we've actually got exactly the same shape as boron trichloride. So how many groups of electrons is this got? 3. Only 3. Okay. So again, we try and work out how many groups. There's only 1, 2, 3. There are no non-bonding. I should say there isn't any non-bonding electrons around the central atom. They're all bonded. Okay. But there's 3 groups. Just so happens this is a single bond group. This is a double bond group. So if we've got 3 of them, hopefully you can work out that they're going to repel, and if these 2 are close, they're going to repel apart. If these 2 are close, they're going to repel apart. But you notice the molecule is absolutely flat. It has to be flat, can't be anything else. What's that shape? Any ideas? Trigonal, trigonal? Planar. Alright? Trigonal planar. So the shape for these is trigonal planar. I use the word flat. Okay?
You just said trigonal plane.
Plane. Trigonal plane is okay, or trigonal planar. But the point is it's a flat molecule. So here is sulfur trioxide. There it is. That's a trigonal planar shape.
Yeah.
And boron trichloride trigonal planar. If we superimpose them, okay, can anybody work out what the bond angle would be? We can do this in ChemSketch, okay, as well. But what do you think the bond angle is going to be if it's going to be uniform around all three? 120, okay. 360 divided by 3. It has to be 120. Can't be anything less, can't be anything more, because VSEPR theory tells us that these are as far apart as possible. The negatives repel, okay. Next one. So that's a trigonal planar arrangement. Now we're going to stop the next one, okay, but the next one is a combination of trigonal pyramid, V-shaped, combined. We'll see how you handle this one. Okay. The last one is based on Mitchell. Yeah.
How many groups were in the first one? 3.
This one?
Yeah.
3. You're talking about the linear one?
Let's talk about the boron.
This one here, 3 groups. 1, 2, 3. 1, 2, 3. This one, 1, 2, 3. So the groups is 3. 3. Let's just say electron groups. There's 3 groups there, and there's 3 groups there. There's no non-bonding. Okay, so they're all bonded. 3, it's got to be trigonal planar. Why isn't that one trigonal planar?
Because it's got an extra one.
Yeah, actually it's got 4 groups. It's got an extra one sitting up here, so that makes it trigonal pyramid. It's good to see that some of you are connecting with that, alright? So, got to be a little bit careful, because at first instance they look the same, okay? And they pretty much look the same, they superimpose, but this one is not flat. This is trigonal pyramid. And again, Mitchell just told us, the electrons here force that down. So the key is, how many pairs, rephrase that, how many groups of electrons are there around the middle atom? There is 4, yeah. That determines the shape. If you can understand that, you understand VSEPR theory and everything else that I'm going to throw at you to do with shape.
That would be a trigonal pyramid.
Trigonal pyramid, correct. Okay, the next one, alright, is what we call, and I'll give you the example down here, here it is. Okay, the typical example that we use to describe this one is methane. Okay, so carbon in the middle, and it's got 4 hydrogens on the outside. Now this is not 90 degrees, okay? It's not 120 degrees either, okay? Because this is a 3-dimensional molecule, this is a flat molecule, okay? This one now goes out into 3 dimensions. Tetrahedral, meaning it's got 1, 2, 3, it's got 4 faces. How many groups of electrons? 4, okay? Here they are, 1, 2, 3, 4. So methane has got 4 groups of electrons, okay? If we go back, trigonal pyramid had 4 groups, water had 4 groups. What was the difference between a V-shaped and a trigonal pyramid? Here's a trigonal pyramid, okay, there it is, tetrahedral, trigonal pyramid, and here's my V-shaped. They're all based on 4. Ethan?
The H2O has 1 less bonded pair. It has 1 more bonded pair.
1 more bond, 1 less, what?
1 less non-bonded pair.
Right.
It has...
It's got 4 bonded. 1 more less.
Say it again?
1 more bonded pair.
1 more bonded pair.
Yes.
Okay, how many bonded pairs has this got?
4.
4. How many bonded pairs has this got?
4.
3 bonded pairs, 2 bonded pairs. Okay. How many groups has this got around the central atom?
3.
many groups? 4 in total, but only 2 are bonded. 4 in total, 3 are bonded, 4 in total, all bonded. Okay? So conceptually then, these are based on the same angle. Use that word angle, okay? Because we're going to get to bond angles eventually. Now, you are not aware of that yet, okay? But hopefully you can work out that if this is a methane molecule, if this hydrogen goes close, okay, this electron cloud and this electron cloud, the bonding, they're going to repel. That's the theory behind VSEPR, okay? So they're going to repel back again. The angle here, all right, and nobody will be aware of this one, but the angle here for this particular shape, which is called tetrahedral, as we mentioned before. So this shape here, the actual angle, although they look different on the board, is 109 degrees, 28 minutes is the bond angle. It's identical. Every single angle for methane is the same. Okay? These two aren't closer to these, they're all identical angle. They have to be. They have to be as far apart from one another in three-dimensional space, and that happens to be the angle that they'll work out to be. If you've only got 3 sets, what's the angle? 120, because it can't be anything else. If I've only got 3 sets or 3 groups, okay, they're going to be 120 degrees, okay, every single time. If you go right back to our linear, if I've only got 1 set, 1 group, it's got to be linear. 1 group, it's got to be linear. 2 only, it's got to be linear. Okay? So all of these shapes that we've worked on, so linear, V-shaped, trigonal pyramid, trigonal planar, tetrahedral, okay, if you can understand all 5 shapes, then you've got the idea about how VSEPR theory works. So I should be able to give you any molecule now, that's what we're going to be doing, and you should be able to tell me what the shape of the molecule is based on those 5 shapes, alright? So we've got linear, V-shaped, trigonal pyramid, trigonal planar, and then tetrahedral, okay? You can hold them in 2 hands virtually, alright? So all 5 shapes of molecules, okay, is what we need to understand. Once we've got that, you can go ahead and do pharmacy and do all sorts of special things, okay? Alright, questions?
What was the degree into the lecture?
It's 109 degrees, 28 minutes. I don't know whether they use minutes in maths anymore, but it's 60 minutes, 60 fractions in 1 degree, okay?
Why are they using minutes?
Minutes, it's a fraction of a degree. It's 109.5 to approximate, 109.5 degrees, okay?